Welcome back, class. So this is the lecture number 2, and the topic for the discussion is factor affecting the stability of a metal complex. So what are the factors which are responsible in order to maintain the stability of a complex? So here mainly three factors are responsible. The first is the properties of central metal ion. Properties of central metal ion. Second is the properties of ligand. And the third one is the metal ligand covalent character presence in the complex. So third is the metal ligand covalent character presence in complex. So these are the three different factors, and under which we will discuss this topic. This is quite a big topic, so in today's lecture I will take only one, and that is the properties of central metal ion. Okay, so the under properties of central metal ion there are several factors based on the central metal ion properties, so we will discuss it one by one. So today only we will discuss the first one. So properties of central metal ion, the first is the size of central metal ion. Size of central metal ion. See, what is the effect of stability on the size? Well, the stability of the complex given by the cation belongs to the same group having the same charge. Okay, we all know that the charge belongs to group. That means in a particular group the charge is similar. So here we are talking about the size of a central metal ion. So the stability, let's take example of stability of a hydroxide complex. Okay, we'll take the example of hydroxide complex. Stability of hydroxide complex given by various group. Okay, so let's talk about the very first group. The first group element is lithium, which has plus charge, and the radius, the size is 0.6. This is only for the showing that what effect of size lithium. And then the second one in that group is sodium. Okay, so which has size is quite bigger than the sodium lithium. Then the next is potassium, of course. So it is again more bigger, so size is 1.33 angstrom. That means the size will be increased as we go down in the group. Size will be what increase. So what effect on the size? I'm not writing the, let's write the whole cesium, and the size is So we can understand easily by this that this is the first group element. First, this is called the alkaline metals actually. So the order of the stability, as size increases, stability will be decreases. Okay, so as we proceed from top to bottoms, the stability of the complex will be decreased for the same group. Point to be noted, it depends on the size. So as the size increase, the stability will be decreased. So what is the uh, stability order here? This will be the more stable, then this one, and then this one. Okay, so this is what the stability order for first A. Now we can take the example of the second group element. So this is again based on the central metal ion size. Okay, and here the charge is +2. Charge is similar for everyone, but as we move from top to bottom, size will increase. So here is beryllium +2, which has a 0.31. Then the magnesium +2, 0.65. Then the calcium +2. Okay, so this will go on. Okay, I'm not writing the rest of the element, but you all know that the size will be increased. Okay, so the trend of the stability order will be like this. That means the beryllium +2 form a more stable complex because of the lesser in size. Okay, let's take some example for +3 charge element. So here we'll take the example of D block elements. Okay, so this is the third B group. Okay, third B group, and here this scandium is the first element. Scandium +3, the size is R 0.81 angstrom. Okay, then just the next after scandium is yttrium y +3. Okay, so it has again 0.93, and then the next is lanthanum La +3. So this is R equal to 1.15. Well, you cannot remember the value, that and that I can understand, but you must know the trend, which depend on the size. Clear? So this is what the effect of central metal ion. See, we can say that size is inversely proportional to the stability as far as the group is concerned. Okay, now the inverse relationship between the size of the central metal ion and the stability of the complex formed, this we can easily explain by the other example. Here I am taking some other example, like we know that Mn +2, then the Fe +2. This is another example I am taking, Mn +2, Fe +2, then the cobalt +2, nickel +2, copper +2, and zinc +2. So we all know that this is the ionic radii. I am writing the value of ionic radii here is 0.91, this is 0.83, this is 0.82. Contraction, the d block element contraction is happening here, that is why the size decreases. Then the nickel is 0.78, then the copper is 0.69, and again zinc will increase, because zinc has completely filled the d orbital. So this is what the size. Now what is the stability order? So of course the stability order will be changed here. Stability order of complex. So manganese plus 2 will be least because it has a bigger in size. So size is always inversely proportional to stability, and so as Fe plus 2 will be stable compared to manganese. Cobalt plus 2 will be stable, nickel plus 2 will be more stable, and here you have to be very careful because here the copper plus 2 is more stable than nickel, okay, but it is greater than zinc, less than zinc and more than nickel, okay. So this is here you have to be careful, and this order, particularly for this order I'm talking, not for this one, okay, there is a train, okay, there is a reverse trend. So this is called Irving William order of stability, okay. This is what Irving William order of stability, only for D block, no, point to be noted. Okay, so this is the first properties. Here we had discussed about the charge, sorry, size of the central metal ion. Okay, let's talk about the uh, charge. What is the effect of charge on the central metal ion? Because here the charge is similar for a group, but if we have a different charge, what will happen in that case? So the second is the charge on the central metal ion. Charge on central metal ion. See, here we are talking about the different charges, okay. We can say that the stability of the complex in metal ion having the same size but different charge, okay. So it will be decreases with the decrease of the charge. That means if there is higher charge, it will show greater stability. Got it? So let's take an example. What different charge on the complex, that means if higher the charge, higher will be the stability, that we can say that. So here we can say that charge on ion is directly proportional to stability. Got it? This is what the simple as. So let's take an example. If I have a TH plus 4 thorium, and the size, of course it will be 0.95 as per the calculated value, okay, which is then yttrium plus 3, R is 0.93. So here the size are almost similar, okay, size is almost similar but charge is different. Calcium plus 2, R is 0.99 angstrom. So as you can see that 0.95, 0.93, 0.99, so almost a similar size of centimeter ion, but charge is different. So higher the charge, higher will be the stability. This is what you have to be answer. Let's take another example. lanthanum plus 3. Okay, so here the size is 1.15 angstrom. Then strontium plus 2, so here the size is 1.13 or 2 almost. We cannot remember the exact value. Then the potassium plus is 1 point. So here I'm not talking about a particular group, here I'm talking about those metal ion which has similar almost a similar size. Okay, so as you can see here that the lanthanum plus 3, strontium plus 2, potassium plus has almost a similar, although this is quite bigger, but we can say that almost. Okay, so here is the order. Lanthanum plus 3 will form more stable complex. Clear? So from first, that means the size of central metal ion, and the second, the charge on central metal ion. Okay, size of central metal ion and the charge on central metal ion. If we combined these two effect, the collectively we can say that it is ionic potential which decide the stability of the complex. Okay, how? So we can say that from first factor and the second factor, uh, we have central metal ion charge. Okay, and then we have ionic radius. So there is another term that is called ionic potential. So what will is the order of stability? Okay, so let's take some example which we had already discussed, that the lithium plus, that means it has what, plus 1 charge. Okay, the radius, ionic radius is 0.60, so the potential will be 1 upon 0.60, so this is 1.6. This is called charge charge and size ratio. This is what charge and size ratio. Similarly, calcium plus 2, it has plus 2 charge, radius is 0.9, so this is 2 upon 0.9, so something like 2.0. Let's take another example of plus 3. So y plus 3, which has plus 3 charge, so radius is 0.93, so 3 by 0.93, so this will give you certainly 3.22. And then plus 4 charge, so thorium plus 4, so the thorium has 0.95, so 4 divided 0.95, so this is something. So as you can see that as ionic potential increases, that means the charge and size ratio increases, the order of stability is also increases. Okay, so this will be the order of stability increases. Got it? So this is what the ionic potential concept. Greater the charge and smaller is the size. What? Greater the charge, smaller is the size, or we can say that the larger the charge and radius ratio of metal ion, greater is the stability. what we can say that greater is the charge, greater is the charge and smaller is the size, and smaller is the size, you can see that. Or larger is the larger is the charge radius ratio, charge radius ratio, higher will be the stability. Greater will be the stability of complex. So this is what the summary of the first and second vector. Okay, we can discuss some example also. Let's take an example of Fe complex. Okay, we have Fe CN6 3 negative and Fe CN6 4 negative. So here F is in +3, here F is in +2. Of course the value of K, that means the stability constant here, is 10 to the power 31 here, and K here is 10 to the power 6. So this will be more stable. Okay, this will be more stable. FeCnO6 3 negative will be more stable. Similarly, we can discuss some more example. So this is what the effect of charge and size of a central metal ion. Well, let's take some more factors. So the next factor, that is the third one, is the metal ion acting as a hard acid and soft acid. Metal ion acting as hard acid and soft acid. So how this will work, let's check it out. See, we all know that there is a concept of HSAB. HSAB, that means hard soft acid base. Okay, I'm not going to in detail, I'm only giving you the theoretical part. Okay, so that with some examples so that you can understand. See, hard acids form stable complex. Okay, but what will be the ligand actually? Okay, acids are the central metal ion, so what will be the ligand? So hard acid form stable complex with ligands which containing the donor site like nitrogen, oxygen and fluorine. Okay, and they can form the less stable complex with the ligands which containing site phosphorus, sulfur and chlorine. So I'm just give you the count of this statement that if we have a hard acid, okay, so this hard acid will form a stable complex and less stable complex. But if we have ligand like nitrogen, oxygen, fluorine, these will be the donating site. Okay, this will be the ligand. Similarly, it will form less stable complex with phosphorus, sulfur, and chlorine. Okay, so if the donor side is phosphorus, chlorine, and sulfur, if the donor side. So this is what the formation of complex in case if it is hard acid, and the uh, this trend will be reverse in case of soft acid. Okay, the trend will be reverse in case of soft acid. Okay, so now for the soft acid, what will happen? For soft acid, the stable complex will form by these ligand which has donor side phosphorus, sulfur, and chlorine. So the soft acid will form stable complex, stable complex, and less stable complex, less stable complex. So what will happen? The side simply reverse. So it will form phosphorus, sulfur, and chlorine, nitrogen, oxygen, fluorine, if the donor side. Sorry. Okay, if the donor side. Okay, so for hard acid, NOF, and for the soft acid, uh, PSL, PSCl. Okay, phosphorus group. So this is what the effect of hard and soft acid. Let's move on for the I know that the video is quite longer, but this is a topic which I have to cover in this because we are discussing only one type of factors, not the all three. So the one type of factor consists of all these things. Okay, let's move for the next factor, that is the fourth one, and here the electrode potential of metal ion will be discuss. Electrode potential of metal ions. So well, what is the effect of electrode potential? See, we all know that we have two types of electrode potential. One is the positive and another one is the negative. So if we have a positive, the large negative electrode potential and large positive electrode potential. So large negative electrode potential, the metal ions which have a large negative electrode potential have a lesser tendency to attract electron. So the complex which is formed is it should be high electronegativity atom. If we have a less, if the metal ion has a lesser tendency, so the ligand must have a higher tendency to get attached, so that would be a high electronegative element. Okay, so large negative electrode potential, that means metal ions having large negative electrode potential. Okay, if it is a large negative electrode potential, that means let's take an example: lithium, then the barium, okay, then the aluminium. So these are the large negative electrode potential ions. So they have a lesser tendency to attract electron, have a lesser tendency to attract electrons. So they required more electronegative atom. Okay, hence in order to form a stable complex, they required more uh, electronegative elements. Got it? So for a stable complex, more electronegative, that means we are talking about the ligand, okay, element, that means like nitrogen, oxygen, fluorine. So the larger negative electrode potentials required uh, uh, larger electronegative element, okay, more negative. Similarly, the greater the ions which have a larger positive electrode potential, okay, second, larger positive electrode potential. So larger potential examples are palladium, platinum. These are the examples of the ion which has a larger positive electrode potential. So they have a higher tendency to attract electron. Okay, they have a greater tendency, have a greater tendency to attract electrons. So if they have a greater tendency to accept electron, that means they will form a stable complex with that ligands that have a highly polarizable coordinate. Okay, so they so form so they form stable complex with what? Least electronegative element like phosphorus, sulfur and chlorine. Least so these are the donor side actually, na? So this is what the electrode potential of a metal ion. Now the last factor, okay, and that is again very important, and this is the called class A and class B acceptor metal. This is, I think, very new for you. Class A and class B acceptor metals. See, this is what the classification of metal based on their accepting tendency. Okay, because this there is a metal ligand interaction, that means the acceptance of ligand by metal. So metals can be classified based on their accepting tendency in three different category. One is class A, one other one is class B, and the third one is called borderline metal also. Okay, so the class A metals, what are the class A metals? I am just writing here the class A metals. So class A metals are actually your hydrogen, Okay, then the alkali metals, alkaline earth metals. So alkali and alkaline earth metals. Then the uh, scandium to chromium, scandium to chromium, aluminium to chlorine, zinc to bromine. Okay, these all are considered as a first class A metals. There are other one, indium is there, tin is there, antimony is there, thallium, not thallium is not, lanthanides and actinides, iodine is there, lanthanides and actinides. Okay, so these are what, these all are considered as a class A metal. Now talking about the class B metal. Class B metal. So class B metals are actually very few. uh, I'm writing here only, like RH is there, PD is there, then the silver, IR, platinum, AU, HG. So these all are what, these all are class B metals. Okay, and the third one is the borderline. Borderline metals. So borderline metals are actually intermediate. Okay, so borderline metals like from manganese to copper, then from titanium to palladium, Mo, molybdenum is there, beryllium is there, Ru is there, Rh is there, not Rh is already we have written, W, tungsten, Re, osmium and cadmium. So these are the borderline metals. So what is the tendency of complex formation for this? See, uh, well, class A metal form stable complex. Class A metals form stable complex with ligand having coordination, that means the coordinating atoms from the second period element, with ligand having the coordinating atoms from second period element. Second period element, that means we are talking about NOF, nitrogen, oxygen, fluorine. Okay, so what will be the order here? Like fluorine will be the highest, then the chlorine, then the bromine, and then iodine. Okay, similarly nitrogen phosphorus. In fact, nitrogen is much more. Okay, arsenic, antimony, and bismuth. So this is the order. This is for class A metal. Okay, now with class B metal the order will be reverse. That means uh, class B metals have the relative stability will be reverse. Okay, so class B metals form, I'm not writing it detail, order will be reverse. Order will be reverse. That means now the class B metal will give you uh, different order, like fluorine, then chlorine, then bromine, then iodine. Similarly, nitrogen, phosphorus, arsenic, then antimony, and then bismuth. So this is from class B metals. And class B metal, generally we are talking about the presence of d electron. Okay, when we talk about the class B metals, that means the class B metals can be characterized by the presence of a number of d electron. Okay, and the third is the borderline. So if they do not belongs to class A and class B, then it will belongs to borderline metals. So the stability constant do not display either the class A or and the class B behavior. Okay, so this is what the different types of factors which are responsible for the stability of the complex. So in this lecture we had discussed the first property and the property of central metal ion. Okay, so in this property of central metal ion we have different categories, like size of central metal ion, then the charge of the central metal ion, then the metal ion which acting as a hard acid and soft acid, then the class A and class B metal, and of course the electrode potential of metal ions. So this all properties belongs to the central metal ion. Okay, in the next lecture we'll talk about the ligand. Thank you so much.